You know, the classic stack overflow. It's a legend in the world of exploits. But when you jump over to a 64-bit system, the whole game changes. I mean, it's the same fundamental flaw, but it's got this whole new set of puzzles you've got to solve. And today, well, we're going to crack that puzzle.
So here's our roadmap for this explainer. We're going to start with what actually makes 64-bit so different. Then we'll look at how functions talk to each other now. After that, we'll tackle the single biggest hurdle. I'm talking about the 0-byte problem. Before we walk through building the actual exploit, we'll even check out an advanced twist and then wrap it all up with why this is still so relevant today.
All right, first up, that big jump to 64-bit. It's really easy to just think, oh, it's just about bigger numbers. But the changes to the architecture go way deeper. They fundamentally change how our programs even operate.
And the most obvious change? It's right here. In the old 32-bit world, the CPU had 8 of these general-purpose registers to work with. But in 64-bit, that number doubles to 16. Seriously, think of it like your workbench just got twice as big. You've got so much more room to work quickly and efficiently.
And here they are, the whole crew. You've got the classics, which are like these tiny, super fast storage spots right on the CPU. Now they're just prefixed with an R for 64-bit. And you also get this whole new set from R8 all the way to R15. This bigger toolkit isn't just for show, though. It actually makes a massive change in how functions work possible.
So all those extra registers, they lead us to our first big puzzle. The old rules for how functions get their instructions, their arguments, have been completely thrown out the window. See, back in the day, it was super simple. If you called a function, every single piece of data it needed was just pushed onto the stack, one by one. Yeah, it was predictable, but it was also kind of slow.
And this is where things get interesting. 64-bit systems are all about optimization. Instead of slowly lining everything up on the stack, the system uses those extra registers like a high-speed delivery service for the first few arguments. It's a huge boost to performance. This table here really lays it all out. The very first argument, it zips into the RDI register. The second one goes into RSI, and so on, all the way through R9. It's only if a function needs a 7th argument or more that the system goes back to the old way of using the stack. And understanding this change, well, it's absolutely crucial for our exploit.
Okay, so we get the new architecture. But now we come to the real heart of the challenge, a hidden trap that can stop a 64-bit stack overflow dead in its tracks. And it all comes down to a single tiny byte.
Now, before I just give it away, think about it for a second. We have an 8-byte address to overwrite. What could possibly go wrong?
Here's your clue. This is a pretty typical 64-bit memory address. Notice anything? I mean, look at all those zeros at the front. Even though the addresses are 64 bits wide, our current systems only really use 48 of those bits. And that means every valid address is going to start with a few 0 bytes.
And here is the whole problem. That 0 byte, or null byte, is a special character. For a lot of C functions, especially the vulnerable stropy Y function we're targeting, a null byte is basically a stop sign. It screams, end of the line, stop copying right here, right now.
And here's that trap in action. So picture this. Your exploit payload is being copied over. It's got your shell code, the actual code you want the machine to run, and your shiny new return address. But the moment strcpy hits that first null byte at the beginning of the address, it just stops. That's it. Your exploit gets cut short and you never get control.
So that seems like a total deal breaker, right? Game over. But the solution is, well, it's baked right into the architecture of the machine itself. It's actually a pretty elegant fix for what feels like an impossible problem.
The solution is something called little endian byte order. It's a bit weird, but here's how it works. We write the address with the zeros at the beginning, right? But the computer actually stores it in memory with the bytes reversed. So those nasty null bytes that were stopping us, they actually end up at the end of the address in memory. This means strcopy copies all the important parts first and only stops when its job is already done. Problem solved.
All right, now that we've sidestepped that whole null byte hurdle, we can get down to business. Let's walk through the actual steps of building and launching our 64-bit Stack Overflow.
It really breaks down into 4 clear stages. First, we've got to find the exact distance to the return address. Then, we build our payload. This has our shell code, a NOP sled, which is just a long runway of no operation instructions to give us a bigger landing zone, and of course, our carefully crafted return address. Third, we aim that address right into our NOP sled, and finally, we launch the attack.
But, a little dose of reality here. This isn't always a perfect science. Memory can shift around a bit,
So it often takes some trial and error. You might have to adjust your return address by a few bytes here and there until you land perfectly on that NOP sled and your shellcode finally runs.
Okay, let's level up. We've cracked the standard exploit, but what happens when the game gets a little harder? Let's take a look at a final, more advanced puzzle that you can definitely run into out there.
So here's the scenario. You find a vulnerability, but the buffer you can overflow is tiny. It's just big enough to overwrite the return address, but there's no way you can fit your shellcode and NOP sled in there. So now what do you do?
The solution here is pretty darn clever. See, when you run the program, your payload is often passed as an argument. That means it's already sitting in memory somewhere else, on the main function stack. So instead of trying to jump into that tiny little buffer, you just find the address of where your payload is already located in memory, and you make that your new return address.
So let's bring this all together. We've picked apart the mechanics, but what's the big picture here? Why does mastering a classic flaw on modern hardware still matter so much? You know, this quote just sums it up perfectly. We're always building new architectures and new defenses, but the underlying logic flaws, they often stick around. By really understanding how these classic exploits adapt, we learn how to build much better defenses and spot weaknesses that other people might miss.
And that leaves us with a final thought to chew on. We just saw how a decades-old vulnerability found a whole new life in 64-bit systems. So the real question is, what fundamental flaws are we writing into our code right now that are going to become the exploits of tomorrow?